A snowball Earth is certainly the most extreme climate change we can conceive the Earth having ever experienced.
The Ice Age is coming. This will Milankovic cycles do to Earth.
It just was the most weird place to expect a glacier.
The Ice Age is coming. This will Milankovic cycles do to Earth. The Ice Age is approaching, and the Milankovic cycles are key to understanding this dramatic shift. These long-term variations in Earth's orbit and axial tilt orchestrate the planet's climate, setting the stage for glacial expansions. As we dive into how these cycles influence Earth's cooling phases, we'll unravel the science behind our planet's icy transformations and what it means for our future.
It was possible that Earth might slip into a climate catastrophe which was covered completely with ice.
Understanding Earth's seasons. What causes them? The Earth's seasons are a fascinating result of the planet's axial tilt and its orbit around the Sun, both of which play crucial roles in the changing climate patterns we experience each year. The Earth is tilted at an angle of approximately 23.5 degrees relative to its orbital plane, a fact that has significant implications for how sunlight reaches different parts of the globe throughout the year. This tilt, combined with Earth's yearly journey around the Sun, creates the variation in sunlight intensity and duration that we know as the four seasons: spring, summer, autumn, or fall, and winter. As Earth orbits the Sun, the axial tilt ensures that different hemispheres are oriented toward or away from the Sun at various times of the year. This orientation is what drives the seasonal changes. During the spring and autumn equinoxes, which occur around March 21st and September 21st respectively, the Sun is positioned directly above the equator. This results in nearly equal day and night lengths across the globe, and these equinoxes mark the transition into spring in the northern hemisphere and autumn in the southern hemisphere. In March and vice versa in September, these equinoxes are moments of balance, where neither hemisphere is tilted more toward or away from the Sun. Around June 21st, the northern hemisphere experiences the summer solstice, a period when it's tilted most directly toward the Sun. This results in the longest day and shortest night of the year in the northern hemisphere, as the Sun appears higher in the sky, and the region receives the most direct sunlight. This abundance of sunlight causes temperatures to rise, leading to the warm, often hot conditions associated with summer. At the same time, the southern hemisphere experiences its winter solstice, where it's tilted away from the Sun, resulting in shorter days, longer nights, and cooler temperatures. Conversely, around December 21st, the northern hemisphere undergoes the winter solstice, when it's tilted away from the Sun. This solstice marks the shortest day and longest night of the year in the northern hemisphere, as the Sun appears lower in the sky and the region receives less direct sunlight, leading to colder temperatures. Meanwhile, the southern hemisphere enjoys its summer solstice with longer days, shorter nights, and warmer weather. The tilt of the Earth's axis means that the southern hemisphere experiences seasons opposite to those in the northern hemisphere. When it's summer in the northern hemisphere, it's winter in the southern hemisphere, and when the northern hemisphere is in winter, the southern hemisphere is basking in summer. This season opposition is a direct consequence of the axial tilt and Earth's position relative to the Sun throughout the year. While the Earth's axial tilt and orbit have remained consistent for millennia, climate change is increasingly influencing the intensity and duration of seasons. Warmer global temperatures, largely driven by human activities, are leading to longer, hotter summers, shorter winters, and more unpredictable seasonal patterns. These changes are already affecting ecosystems, agriculture, and human communities around the world. Understanding the mechanisms behind Earth's seasons is more important than ever, as the impact of climate change on these natural cycles becomes more pronounced. As we continue to study and understand Earth's climate system, it's crucial to consider how these changes may alter the familiar rhythm of the seasons and what that means for life on our planet. How Earth's tilt affects seasonal changes. Earth's tilt is the primary factor responsible for the seasonal changes we experience throughout the year. The planet is tilted at an angle of approximately 23.5 degrees relative to its orbit around the Sun, And this axial tilt is what causes different parts of the Earth to receive varying amounts of sunlight. As it moves through its annual orbit, these variations in sunlight intensity and duration are what give rise to the distinct seasons of spring, summer, autumn, and winter. As Earth orbits the Sun, the axial tilt causes the northern and southern hemispheres to be oriented toward or away from the Sun at different times of the year. When one hemisphere is tilted toward the Sun, it experiences summer, characterized by longer days, shorter nights, and more direct sunlight. The increased sunlight results in warmer temperatures. Conversely, when the same hemisphere is tilted away from the Sun, it experiences winter, with shorter days, longer nights, and less direct sunlight, leading to cooler temperatures. This tilt is responsible for the solstices and equinoxes, key moments in Earth's annual journey that mark the changing of the seasons. The summer solstice occurs around June 21st, when the northern hemisphere is tilted most directly toward the Sun. On this day, the northern hemisphere experiences the longest day and shortest night of the year, as the Sun reaches its highest point in the sky. The increased exposure to sunlight during this time is what makes summer the warmest season of the year in this hemisphere. Meanwhile, the southern hemisphere experiences its winter solstice, with shorter days and longer nights. The winter solstice occurs around December 21st, when the northern hemisphere is tilted away from the Sun. This results in the shortest day and longest night of the year, with the Sun appearing lower in the sky and providing less direct sunlight. This reduced solar energy leads to the colder temperatures associated with winter. At the same time, the southern hemisphere enjoys its summer solstice, with longer days, shorter nights, and warmer weather. The spring and autumn equinoxes, occurring around March 21st and September 21st respectively, are moments of balance, when the Sun is positioned directly above the equator. During these times, both hemispheres receive roughly equal amounts of daylight and darkness. The spring equinox heralds the beginning of spring in the northern hemisphere, while the autumn equinox marks the start of autumn. While Earth's axial tilt has remained consistent, climate change is beginning to alter the intensity and duration of seasonal changes. Rising global temperatures are leading to longer, hotter summers and shorter, milder winters. These shifts in seasonal patterns are impacting ecosystems, agriculture, and weather patterns worldwide. As the effects of climate change become more pronounced, understanding how Earth's tilt influences the seasons is critical for predicting and adapting to these changes. Seasons in different parts of the world. Seasons vary significantly across different parts of the world, shaped by Earth's axial tilt, latitude, and geographical features. While most regions experience the classic four seasons, spring, summer, autumn, and winter, other areas have unique seasonal patterns due to their location on the globe. In temperate regions, which lie between the tropics and polar circles, the year is typically divided into 4 distinct seasons. These regions, including much of North America, Europe, and parts of Asia, experience noticeable changes in temperature and weather throughout the year. Spring is marked by warming temperatures and blooming vegetation, while summer brings long days, high temperatures, and abundant sunlight. Autumn, or fall, is characterized by cooler temperatures and the shedding of leaves, and winter brings the coldest temperatures with snow and ice, common in many areas. These seasonal changes are driven by Earth's axial tilt. As the Earth orbits the Sun, different parts of the temperate regions receive varying amounts of sunlight, leading to the temperature fluctuations that define each season. For example, during the summer solstice in June, the northern hemisphere is tilted toward the Sun, resulting in longer days and warmer temperatures. Conversely, during the winter solstice in December, the northern hemisphere is tilted away from the Sun, leading to shorter days and colder temperatures. In tropical regions located near the equator, the concept of 4 distinct seasons doesn't apply. Instead, these areas, including much of Africa, Southeast Asia, and Central America, experience 2 primary seasons: the wet season and the dry season. The wet season, often referred to as the monsoon season, is characterized by heavy rainfall, high humidity, and lush vegetation growth. This period is crucial for agriculture and water resources. The dry season, on the other hand, brings less precipitation, lower humidity, and often higher temperatures. These seasonal patterns are influenced by the migration of the Intertropical Convergence Zone, ITCZ, a band of low pressure that moves with the Sun. As the ITCZ shifts north and south throughout the year, it brings rain to tropical regions, creating the wet season, When the ITCZ moves away, these areas experience the dry season. In the polar regions, which include the Arctic and Antarctic, the seasonal cycle is marked by extreme variations. In daylight, instead of 4 seasons, these regions experience polar day, midnight sun, and polar night. During polar day, which occurs in the summer, the sun remains above the horizon for 24 hours, leading to continuous daylight. This period can last for several months, depending on the location. Conversely, during polar night in the winter, the sun does not rise above the horizon, resulting in continuous darkness for several months. While these seasonal patterns have remained consistent for centuries, climate change is beginning to alter the timing, intensity, and characteristics of seasons across the globe. For example, warmer global temperatures are causing longer summers, shorter winters, and unpredictable rainfall patterns in tropical regions. In polar areas, the melting of ice due to rising temperatures is also affecting the duration of polar day and polar night. These changes are having profound effects on ecosystems, agriculture, and human societies worldwide, making it essential to understand and adapt to shifting seasonal dynamics in different parts of the world.
The misconception: distance from the sun and seasonal changes. A common myth is that the distance between Earth and the sun determines our seasons. Many people believe that when Earth is closer to the sun, it should be hotter, and when it's further away, it should be cooler. This notion is understandable but inaccurate. The real reason behind seasonal changes lies not in our distance from the sun, but in the tilt of Earth's axis.
Earth's orbit around the sun is slightly elliptical, meaning its distance from the sun varies throughout the year. However, this variation is relatively minor, ranging from about 91.4 million miles, 147.1 million kilometers at its closest, perihelion, in early January, to about 94.5 million miles, 152.1 million kilometers at its furthest, aphelion, in early July. The difference in solar energy received due to this distance variation is minimal compared to the effect of Earth's axial tilt. The true driver of seasonal changes is the tilt of Earth's axis, which is approximately 23.5 degrees relative to its orbital plane. This tilt causes different parts of Earth to receive varying amounts of sunlight throughout the year. During the Northern Hemisphere summer solstice, which occurs around June 21st, the North Pole is tilted toward the sun, resulting in longer daylight hours and more direct sunlight. Conversely, during the winter solstice, around December 21st, the North Pole is tilted away from the sun, leading to shorter daylight hours and less direct sunlight. Similarly, the Southern Hemisphere experiences its summer and winter at opposite times of the year due to its axial tilt. The equinoxes occurring around March 21st and September 23rd mark the points where daylight and darkness are roughly equal worldwide, as neither hemisphere is tilted toward or away from the sun. The role of Earth's axis in creating seasons. The changing seasons are a result of Earth's axial tilt, rather than its proximity to the sun. This tilt, which is approximately 23.5 degrees relative to Earth's orbital plane, plays a crucial role in the variations of temperature and daylight that define the seasons. As Earth orbits the sun, its axis remains pointed in the same direction toward the North Star. This means that during different times of the year, different parts of Earth are tilted toward or away from the sun. This axial tilt is the primary factor responsible for changing seasons, not the distance between Earth and the sun. During the Northern Hemisphere summer solstice, around June 21st, the North Pole is tilted toward the sun. This results in longer daylight hours and more direct sunlight, creating warmer temperatures. The sun's rays strike this part of the Earth more directly, increasing the intensity of the sunlight and heating the surface more effectively. Conversely, during the winter solstice, around December 21st, the North Pole is tilted away from the sun. This results in shorter daylight hours and less direct sunlight, leading to cooler temperatures. The Southern Hemisphere experiences its summer and winter at opposite times of the year due to its axial tilt. For example, while the Northern Hemisphere is basking in summer's warmth, the Southern Hemisphere is experiencing winter, and vice versa. Equinoxes occurring around March 21st and September 23rd are the times when daylight and darkness are nearly equal. During these periods, Earth's axis is neither tilted toward nor away from the sun, so both hemispheres receive nearly equal amounts of sunlight. These moments mark the transition between the extremes of summer and winter and lead into the spring and fall seasons, respectively. This axial tilt also affects the length of the day. For instance, during summer, the tilt causes the sun to take a longer path across the sky, resulting in longer daylight hours. In winter, the sun's path is shorter, leading to shorter days. This variation in day length, combined with the angle of sunlight, impacts both the intensity and duration of solar energy received at different latitudes, further influencing temperature and weather patterns.
Introducing Milankovic cycles, a deeper look at Earth's long-term climate changes. Milankovic cycles, named after Serbian mathematician Milutin Milankovic, offer a profound understanding of Earth's long-term climate variations. These cycles consist of three main components: eccentricity, obliquity, and precession. Eccentricity describes the variation in the shape of Earth's orbit around the Sun, which cycles between more circular and more elliptical forms over about 100,000 years. This change impacts the distance between Earth and the Sun, thereby affecting the amount of solar energy Earth receives throughout the year. Obliquity refers to the tilt of Earth's axis relative to its orbital plane, which oscillates between 2.1 and 24.5 degrees over a 41,000-year cycle.
This axial tilt influences the severity of seasonal contrasts. Greater tilt results in more extreme seasonal differences, while a lesser tilt leads to milder seasons. Precession involves the wobble of Earth's rotation axis, with a cycle lasting approximately 26,000 years. This wobble alters the timing of seasons in relation to Earth's orbit, affecting seasonal intensity in different hemispheres. Recent advancements in climate science using ice core data, sediment records, and sophisticated climate models have enhanced our understanding of how these astronomical cycles have driven major climate shifts, including the onset and retreat of ice ages. These studies reveal that while Milankovic cycles were crucial in shaping past climate patterns, contemporary climate trends are influenced by a complex interplay between these natural cycles and human activities. This comprehensive view of Milankovic cycles underscores their significance in studying Earth's climatic history and ongoing climate dynamics. The first cycle, orbital eccentricity and its impact on Earth. Orbital eccentricity refers to the measure of how much an orbit deviates from being a perfect circle. It ranges from 0, indicating a circular orbit, to values approaching 1, which signify highly elliptical orbits. Earth's orbit around the Sun, known as the ecliptic, has an eccentricity of about 0.0167. While this might seem minor, it has significant effects on Earth's climate over long periods. Recent studies have highlighted the role of orbital eccentricity in Earth's climatic cycles. The current eccentricity is relatively low, leading to a nearly circular orbit. However, this isn't always the case. Over tens of thousands of years, the eccentricity varies due to gravitational interactions with other celestial bodies and the Sun. These variations influence the intensity and distribution of solar energy reaching Earth. The Milankovic cycles, named after the Serbian mathematician Milutin Milankovic, describe these long-term variations in Earth's orbit and tilt. Orbital eccentricity is one component of these cycles, affecting Earth's climate by altering the distance between Earth and the Sun throughout the year. When eccentricity increases, Earth's orbit becomes more elliptical, causing more pronounced seasonal changes. This can lead to cooler summers and warmer winters in the Northern Hemisphere, influencing ice sheet growth and retreat. Current research incorporates data from space missions and advanced climate models to understand these impacts better. For example, NASA's ongoing observations of Earth's orbit and climate data from satellites help scientists track these changes more precisely. Recent studies suggest that while Earth's orbit is currently in a more circular phase, this will change in the future, potentially impacting long-term climate patterns. Furthermore, the interaction between orbital eccentricity and other Milankovic cycles such as axial tilt and precession compounds its effects on climate. These cycles work together to influence the timing and intensity of ice ages. The current low eccentricity contributes to a relatively stable climate, but as it increases over millennia, we might see more significant shifts in temperature and ice distribution.
The second cycle, changes in Earth's axial tilt. Earth's axial tilt, the angle at which the planet's axis is tilted relative to its orbit around the Sun, is a key factor in determining the planet's climate. Currently at about 23.5 degrees, this tilt influences the intensity and distribution of sunlight that different latitudes receive, thereby affecting seasonal variations and climate patterns across the globe.
The axial tilt is not a static feature but undergoes gradual changes over extensive periods through a process known as axial precession. This phenomenon, often referred to as the second cycle within the context of Milankovic cycles, oscillates between 22.1 and 24.5 degrees, approximately every 41,000 years. Such variations in tilt have a profound impact on Earth's climate by altering the strength and distribution of seasons. When the tilt reaches its maximum, seasonal extremes become more pronounced, leading to hotter summers and colder winters. Conversely, a smaller tilt results in more moderate seasonal variations, with milder summers and winters. Recent research, propelled by advancements in satellite technology and analysis of ice core samples, indicates that Earth's axial tilt is currently in a phase of gradual decrease. This reduction, although occurring slowly, holds significant implications for global climate patterns. For instance, a continued decrease in the tilt could lead to cooler summers and milder winters over the coming millennia, potentially influencing patterns of glaciation and long-term climate trends. This shift could have cascading effects on global weather systems and ecosystems, highlighting the interconnected nature of Earth's climatic processes. Additionally, current studies underscore the interconnectedness of Earth's axial tilt with other components of the Milankovic cycles, such as orbital eccentricity, the shape of Earth's orbit around the Sun, and axial precession, the wobble of Earth's axis. These cycles collectively contribute to long-term climate variations and are instrumental in understanding historical climate shifts, including ice ages. The interplay between these cycles can amplify or mitigate the effects of each cycle, leading to complex climate outcomes. Understanding these changes is crucial for predicting future climate scenarios. The current phase of decreasing axial tilt might offset some warming effects projected by other climate models. However, human activities, particularly greenhouse gas emissions, remain a significant driver of contemporary climate change, potentially overshadowing the effects of natural cycles. As scientific research continues to evolve, monitoring these cycles will be vital for developing accurate predictions and managing long-term climate impacts. The third cycle, axial precession and its effects. Axial precession, the third cycle in the Milankovic cycles, refers to the gradual wobble in Earth's rotational axis. This precession occurs over a period of approximately 26,000 years and results from gravitational forces exerted by the Sun and Moon on Earth. As the axis wobbles, it shifts the orientation of Earth relative to its orbit around the Sun, influencing the timing of seasons and climatic patterns. Currently, axial precession causes shifts in the alignment of Earth's hemispheres, with the Sun impacting seasonal extremes. For example, it alters the timing of solstices and equinoxes, which affects the intensity and duration of seasons. When precession aligns Earth's axis with the Sun's position differently, it can lead to changes in temperature distribution across the planet. This cycle interacts with other Milankovic cycles, such as changes in eccentricity, Earth's orbit shape, and axial tilt, to influence long-term climate patterns. As a result, axial precession plays a significant role in driving the natural variability of Earth's climate, contributing to the onset and retreat of ice ages and other significant climatic events over millennia.
As the Ice Age approaches, Milankovic cycles will reshape our planet's climate in ways we can only imagine. To stay updated on this fascinating topic, click the video popping up on your screen, like, and subscribe for more.